Hello, today we are going to discuss about Unit 1 of PDC, that is linear wave shaping. Linear wave shaping is related to linear circuits or linear networks. Both are same only. A linear circuit consisting of linear elements. Examples of linear elements are R, L and C. If a circuit consisting of either resistor or inductor or capacitor or any combination of them, then the circuit is treated as linear circuit or linear network. Linear network behaves differently for different inputs. For example, if you are applying sinusoidal input for a linear circuit, then the output is also of sinusoidal in nature. So that means wave shape is preserved at the output of linear network when a sinusoidal input is applied. But only the change is amplitude may be reduces, as well as there may be a phase shift introduces between output and input. And if you apply a non-sinusoidal input to a linear network, then the output is not same as input. That means at the output, wave shape is not maintained when a non-sinusoidal input is applied. So definitely the output is different from the input, and we are going to study how the output is going to be get changes when a non-sinusoidal input is applied to a linear network. That study is called as linear wave shaping. The definition of linear wave shaping is related to linear circuit when applied with non-sinusoidal signals. So it is defined like this. Linear wave shaping is the study of change in output wave shape or waveform. Study of change in output waveform of a linear circuit when a non-sinusoidal signal, when a non-sinusoidal input is applied. So we know that when a non-sinusoidal input is applied, output is gets changed. So how the output is getting changed, that if you are going to study, that study is treated as linear wave shaping. And if you apply sinusoidal input, output is also sinusoidal, no need to study, only we should know what will be the gain, what will be the phase shift, because only two things gets changed. The amplitude is going to be gets reduces, as well as phase shift is going to be introduces. Simple linear networks which we are going to study are RC network, RLC network and RLC network. So we will see how the output maybe looks like. Okay, so make it as 0 and this is 1 and 2. Okay. So as the input is applied, you may get the output response like this. This is voltage input and it is voltage output. So there may be a phase shift between output and input. Amplitude is also different from this one. So this amplitude, if you are making it as V, it may not be V, this may be V1. V and V1 are going to be different. So magnitude gets changes, as well as there may be a phase shift introduces. Since it is a capacitive network, RC, this is the output for the RC network. RC network. So this is the output when it is taken across capacitor. So if the output is taken across capacitor, this type of waveform you may get. And if the output is taken for the same RC circuit, if you are taking output across resistor, then this is also for RC network, for the same RC. But if you are taking output across resistor, it's having a phase angle, something as pi 1. This is again phase angle between output and input. So for resistor, output lags input. For capacitor, output leads input. So today we are going to study response of linear circuit, especially RC circuit we are going with. response of RC circuit for a sinusoidal input. How the magnitude is not going to change, how the magnitude gets changed, how the wave shape is maintained, and how the phase angle is going to be introduced. These things we are going to study today. Next, now we are studying about the RC network. So RC network is a simple network which consisting of only two elements. One is R, the other is C. If you look at R and C elements, you can connect either in this way or in this manner. Since both are in series, you can interchange the elements. Okay, and you can apply the input signal, sinusoidal signal over here. V input you can apply. So the response is going to be same whether the elements are going to be connected in this manner or in this manner, because they are in series. Remember it. Okay, so if you are taking output across capacitor, then it is called as low pass RC circuit. If you take output across resistor, for the same circuit, if you take output across capacitor, it is called as low pass RC circuit, and if you take output across resistor, it is called as high pass RC circuit. Same circuit, it consisting of only two elements, resistor and capacitor. Okay, but once if you are taking output across capacitor, that will be treated as low pass RC circuit. If you are taking output across resistor, it is high pass RC circuit. So the same circuit can be written like this. The well-known circuit. Okay, this is R and C, where the input you are going to apply here. So now you are taking output across capacitor. V0 is nothing but Vc. So this is low pass RC circuit. It acts as low pass filter. Low pass filter. And if the well-known circuit for this one is this is. Here also both are in series only. Now you are taking output across capacitor. V0 is nothing but VR. Voltage across resistor is now output for the same circuit. You are applying the same input. Okay, then it is called as high pass RC circuit. It acts as high pass filter. So low pass filter allows low frequencies, okay, up to a certain frequency which is called as upper cutoff frequency, and high pass filter allows all high frequency signal starting from a lower cutoff frequency. This is the difference. Since we are going with same RC circuit, but where you are taking output is important. So first we will study about the low pass RC circuits. Later we will go for the high pass RC circuit. Okay. So response of low pass RC circuit for a sinusoidal input is the next topic for us. No. Response of low pass RC circuit for a sinusoidal input. This is R and C elements. Okay. Sinusoidal input is going to be an input with a single frequency F. So we are interested in frequency response of this circuit. That's why I am considering the S domain, Vi of S and V0 of S. Resistor is going to be same in frequency domain since it is frequency independent, and capacitor can be represented as C is replaced with 1 by SC in frequency domain. So using KVL, the total input voltage is applied across R as well as 1 by SC. So if you require output voltage across capacitor, by using Kirchhoff's voltage law, we can write voltage drop across this one divided by total voltage. So 1 by SC divided by R plus 1 by SC into Vi of S. We are interested in only magnitude. So V0 of S by Vi of S is equal to 1 by 1 plus SCR. If you take SC common, SC gets cancelled in numerator and denominator. So 1 by 1 plus SCR you will get. S can be represented as J omega. Replace S with J omega. Omega is 2 pi f. So replace omega with 2 pi f. So out of this 2 pi f RC, keep f as it is, and 2 pi RC can be written as f by 1 by 2 pi RC. If you take this 2 pi RC towards numerator side, again you are going to get the same term. So this I am replacing with a special notation which is FH. I am replacing with a special notation which is FH. where fh is nothing but upper cutoff frequency, which is equal to 1 by 2 pi RC. Remember that one. fh is going to be constant for a given RC circuit. fh is constant for given RC circuit. Given RC circuit is nothing but for given R and C values. For given R and C values. So if R and C values are not varying, that means upper cutoff frequency of the circuit is fixed. Okay. Whereas the input signal can have any frequency. So whether it has to pass or it has to stop, that is totally depending on fh value. If the input frequency is less than fh, it will be passed through the circuit. If the input frequency is greater than fh, it is stopped by the circuit. That we will see. Okay. So this is the transfer function. We can call this term as transfer function of low pass RC circuit. V0 of s by Va of s is equal to 1 by 1 plus Jf by Fh. Now, from the transfer function, we can see transfer function includes J term. That means it is complex in nature. So, any complex equation can be represented in polar form like this. If you are going with A plus JB, you can write it as equivalently, okay, magnitude as well as phase. Equivalently, where m is equal to, you can write it as square root of a square plus b square. Pi is equal to phase angle tan inverse b by a. So using this relation, I am going to convert it into polar form. Polar form will be mainly consisting of magnitude and phase. Magnitude is V0 by Vi, okay, 1 by 1 plus f by fh whole square. Okay, 1 by 1 plus f by fh whole square, square root of 1 by 1 plus f by fh whole square. And pi is equal to angle of V0 by Vi. That means minus tan inverse f by fh. If you have only this term, then you will get it as tan inverse imaginary by real. By the time it is positive. But that tan inverse you are going to take towards numerator. Then it will be introducing a negative sign. Minus tan inverse f by fh. So f is nothing but, now you must understand 2 points. What is meant by small f, what is meant by f suffix h. Okay, if you understand the difference, it is very easy. Since we are talking about a low pass RC circuit which consisting of 2 elements, okay, as R and C values are constant, you can define fh. fh is equal to 1 by 2 pi RC. That means it is circuit related. Upper cutoff frequency is based on the circuit. For the given circuit, for the given R and C values, you can easily calculate upper cutoff frequency. Whereas f means small f. Small f is related to V in of f. J omega V in of s you have written. S means j omega is j2 pi f. So it is related to the frequency of the input signal. Small f means frequency, input signal frequency. Frequency of input signal. Applied input sinusoidal signal is having a frequency f. Remember that one. That f can be anything from 0 to infinity. Because we don't know which input signal frequency you are going to apply. So by that time this is generalized as f is varying from 0 to infinity. So as f is 0 to infinity, it varies. What happens to magnitude? What happens to phase angle? That we are going to study. At f is equal to 0, substitute f value. That means input signal is 0. That is simply it is DC signal. Okay. For this one, the magnitude is 1. And phase angle, tan inverse 0 means 0 degrees. So there will be no phase difference whenever you apply a DC signal. DC signal will appear as it is at the output side. Whatever the signal you are applying, that signal will appear at the output side. Because V0 by Vi is equal to 1, that means V0 is equal to Vi. Okay. That means V0 is equal to Vi. Same signal appears at the output side with 0 degrees phase shift. Next, as f increases, as input signal frequency is increasing, but it is lesser than the upper cutoff frequency. Remember it. So as it is lesser than upper cutoff frequency, f by fh leads a small value. Since f is small, fh is large. So small value, if you are taking, let us assume it is 0.1. 0.1 whole square is 0.01. Okay. So always square of smaller value lesser than 1 will give very small value. That very small value can be neglected compared to 1. So this will be approximately equal to 1. But strictly speaking, V0 is lesser than Vi. It's going to decrease. As f increases, V0 is going to be gets decreases. Okay. And next, when f is equal to fh, when f is equal to fh, f by fh is equal to 1, 1 square is 1, that means 1 by root 2 you will get. 1 by root 2, 1 by root 2 means, okay, that means 0.707. So V0 is equal to 0.707 times of V input, that is 70.7% of input value. If you apply 1 volt, you will get 0.707 volts at the output. So if you are writing phase angle at f is equal to fh, okay, f by fh is equal to 1, tan inverse 1 is minus 45 degrees. Minus 45 degrees. So pi value is changes from, okay, 0 degrees to 45 degrees. I am going with magnitude of pi. That means the pi value is in negative. So it is between 0 to minus 45, the meaning. And exactly we can calculate the value pi. So I am writing it as minus 45 degrees rightly. Next, as f increases, but now f is greater than fh. F is greater than fh means f by fh is greater than 1. In this case is f by fh is less than 1. As f by fh is greater than 1, so this will be a large value, and square of that large value is very large, and you can neglect this one. So 1 by very large. 1 by very large is nothing but V0 by Vi is very small. So it will be less than 1 by root 2. Okay. V0 by V input is going to be gets reduces. V0 by V input is reduces. Okay. From this 1 by root 2, as f increases, its value even further reduces. As f becomes infinity, it becomes 0. As f becomes infinity, it becomes 0. So always as the frequency is between fh and infinity, then the magnitude value is between 1 by root 2 and 0. Okay. So here output will be 0. Here output is reduces. Next, in the same way, if f is equal to infinity, pi can be written as minus 90 degrees, because tan inverse infinity, f by fh, when f is equal to infinity, infinity by something is infinity, tan inverse infinity is 90 degrees. So pi is 90 degrees and the magnitude of pi is between 90 degrees and 45 degrees. What actually this minus sign indicates? That is very, very important. Okay. This minus sign, strictly speaking, we can remove this minus sign if you say output leads inputs. That minus sign says output waveform is leading the input waveform. If the sign is not there, if it is, for example, if it is plus, then output lags input, otherwise input leads output. So this minus sign specifies that output is leading input by this much angle. If you say pi is equal to 45 degrees, that means output leads input by 45 degrees. We don't call again negative. Okay. Minus 45 degrees means output leads input by 45 degrees. Minus 90 degrees means output leads input by 90 degrees. Like this we need to specify. So this is how the magnitude is going to be changes as well as phase angle is changes when frequency is changing from 0 to infinity. So if you observe, okay, if you observe this column, what you understood? If you observe this magnitude column, always the value of magnitude is going to be constant. Constant for a given frequency, constant for a given frequency, okay, and for a given FH. So if you know the FH value, if you know the input signal frequency, then definitely your magnitude is going to be constant. Whenever you are going to get a constant magnitude, then you can write it as V0 by Vi is equal to some constant, that you can write it as V0 is equal to constant multiplied by V input. V input is sinusoidal signal, you can write it as V sin omega t, and if you multiply with constant, suppose x is going to be a constant, x V times, so only the magnitude of sinusoidal signal is going to be gets changed, not the frequency. That means same sinusoidal in shape is maintained at the output side, the magnitude is gets differed by the V0 by Vi value, that is whatever the magnitude you are getting, that will be multiplied by the input signal. Okay. Always the magnitude of LPRC circuit for a sinusoidal input is yielding a constant value for any given input frequency or for any given cutoff frequency. That means simply input signal is multiplied by that constant. Whenever a sinusoidal input is multiplied by a constant, its shape is preserved, only the amplitude gets changes. As well as there may be a small phase shift introduces, okay, depending on the input frequency and cutoff frequency. That is also we have seen, which is in the second column, pi. So the maximum phase shift introduced between output and input is minus 90 degrees, and minimum phase shift introduced between output and input is 0 degrees. Okay, phase shift introduced when the input signal frequency is exactly equal to upper cutoff frequency is minus 45 degrees. These are the important points you should know. Okay, so from this one we can confirm that output of LPRC circuit, that is response of LPRC circuit, is same as input signal when a sinusoidal input is applied. Okay. Now we will draw the magnitude response and phase response. Magnitude response is magnitude versus frequency, phase response is phase versus frequency. Okay, so magnitude response is at most you are going to get it as 1 for DC signal at f is equal to 0, and from that one the value is going to be gets reduces towards 0. We know that one, it is acting as low pass filter, it passes all the frequencies up to FH, circuit upper cutoff frequency FH. So first indicate the FH point, and at this point you must get 0.707. Otherwise first you draw a circuit which resembles this one, and where this is this is 0.707. Okay, so for the frequency less than FH, so for the frequencies less than FH, the magnitude is greater than or equal to 70.7% of its maximum value, and for the frequencies greater than FH, that is this portion, okay, magnitude is lesser than 0.707, and as frequency increases it may approach 0. This is magnitude response. If you observe the phase response, for DC signal it is 0 degrees phase shift, and phase shift introduced at f is equal to FH is minus 45, so minus 45 degrees, and at f is equal to infinity minus 90 degrees. So simply draw two horizontal lines at 45 and at 90, and we can draw the phase shift which is starting from, okay, So it is not linear strictly speaking. So at which it is touching, this point is treated as FH. For frequencies less than FH, if the input signal frequency is less than FH, then the phase angle is between 0 and minus 45 degrees. If the input signal is exactly equal to FH, phase angle is minus 45. If the input signal is greater than FH, then the phase angle is between minus 45 to minus 90 degrees. Remember that one, it is not linear. So we have seen magnitude response as well as phase response of LPRC circuit, low pass RC circuit, when a sinusoidal input is applied. Generally, we know the definition of bandwidth. The formal definition of bandwidth is the range of frequencies over which the gain is greater than or equal to 70.7% of its maximum value. This is the definition of bandwidth. From this definition of bandwidth, can you calculate the bandwidth of low pass RC circuits? So bandwidth can be calculated from the frequency response, that too from the magnitude response. So bandwidth of this circuit, bandwidth is the range of frequencies over which the magnitude is greater than or equal to 70.7% of its maximum value. If this is the maximum value, then 70.7% is nothing but this one. So entire this duration is treated as bandwidth because this range of frequencies are having magnitude response greater than 7.707. So this is lowest frequency and it is highest frequency. This will be treated as FL, this will be treated as FH in terms of bandwidth. So generally we know that one, FH minus FL is nothing but bandwidth. For FH is nothing but FH minus FL means 0 in case of low pass RC circuit. So bandwidth of low pass RC circuit is exactly same as upper cutoff frequency. For a low pass RC circuit, bandwidth is upper cutoff frequency itself. Okay. This is one more important point you should remember. Bandwidth of low pass RC circuit is FH itself. How can output wave shape of low pass RC circuit is same as input wave shape? Already we discussed this one. From the magnitude column, always the magnitude is going to get it as constant, and that constant is multiplied by input signal and appears at the output side. Input signal is sinusoidal signal. When it is multiplied by a constant, again the result is sinusoidal only, but the magnitude gets changed by that constant value. Okay, so definitely output wave shape of low pass RC circuit is same when the input signal is sinusoidal. So conclusions from this response of LPRC circuit for a sinusoidal input are given like this. First conclusion, low pass RC circuit can act as low pass filter with upper cutoff frequency as FH. Because this low pass RC circuit is giving more magnitude for the frequencies less than FH and less magnitude for the frequencies greater than FH. That means F less than FH is treated as pass band, F greater than FH is treated as stop band. So FH is the upper cutoff frequency, up to that frequency it passes. And bandwidth of low pass RC circuit is FH. FH is nothing but upper cutoff frequency, which can be calculated if you know R and C values of the given circuit. So from this definition 1 by 2 pi RC, FH can be known. FH is constant if R and C values are constant. And response of linear circuit is always sinusoidal in nature when the input signal is sinusoidal. And fourth one is wave shape at the output of low pass RC circuit is not maintained, that is not same as the input wave shape if the input is non-sinusoidal. So these are the important conclusions related to response of low pass RC circuit for a sinusoidal input. In the next class, we will see response of low pass RC circuit for a step input. But before studying that one, we will see the importance of capacitor in RC circuits. how a capacitor gets charged, how a capacitor gets discharged. Okay, what are the function of capacitor? All those things we will study. Later we will go for the response of low pass RC circuit for a step input. Thank you.